Hey everyone, today we're going to talk about logarithms. Now, logarithms can feel very unintuitive and foreign to someone who's first encountering them, so we're going to try and build them up from something that might be a little bit more familiar. Let's say we've got a function, we'll call it digit, that takes in a positive whole number and puts out the number of digits it has minus 1. So, in mathematical terminology, we have digit from the positive or positive whole numbers to the natural numbers, which is positive whole numbers plus 0. And we'll just list out a couple of examples of what digit does to things, right? Digit of 9, 9's got one digit, so we'll subtract 1, digit of 9 is 0. Digit of 99, well, 99's got two digits, so we'll subtract 1, and digit will be 1. Digit of 4,789, well, 4,789's got four digits, so we'll subtract 1 and get 3. Alright, nothing life-changing here. Now the question is this digit function useful? What kind of cool properties does it have? For example, if we combine two numbers by multiplying them, what happens to the number of digits, right? Do we know anything about the digit of the product if we know something about the digit of the two things we put into the product? Well, let's think, right? Here I've got a million times 10,000. Digit of a million is equal to 6. And digit of 10,000 is equal to 4. And digit of a million times 10,000, or 10 billion, turns out to be equal to 10. And you can tell that just by counting the number of zeros, right? The number of digits past the first one is just all these different zeros. Now you might notice that 6 plus 4 is 10. Now in this example, when we have these perfectly round numbers and digit does nothing more than count the zeros, it's pretty obvious why that happens, right? If we're multiplying round numbers like this, well, we're just adding the number of zeros to each other, and the same thing gets mirrored in digit. Now, is that always true? Let's take a look. Now, digit of 9 times 99 is digit, I already did this on a calculator, of 891. And that equals to the number of digits, so 3 minus 1, and that is 2. Now notice that before we had digit of 9 equals 0, and digit of 99 equals 1. So it's not equal to the sum of the two digits. On the other hand, if we got digit of 1 times digit of 11, we get digit of 11, which is equal to 1. And in this case, we have digit of 1 equals 0, digit of 11 equals 1, and they do add up. Moving on to a bigger example, we've got digit of 748 times times 4,126, which turns out to be equal to digit of about 3 million, which gives us the answer of digit to be 6, because 3 million has 7 digits, so we subtract 1, get 6. Meanwhile, digit of 748 is 2, and digit of 4126 is 3. So let's take a look at the pattern here, right? Up here, we had digit of the product is 2. And the sum of the digits is 1. Up here, it was 1, the sum was 1. And down here, the sum was 6, or sorry, the digit of the product was 6, and the sum is 5. 2 plus 3, 5. So every time we've either gotten the same number of digits or one more than the sum of the digits, right? And it turns out that this will always happen. Why does it always happen? Well, the reason it's always so close to the sum is because of similar logic to up here, right? When you're multiplying these two numbers, you're kind of adding the number of places they have almost. The reason we sometimes get an extra digit is because some numbers are in some sense closer to the next digit than others, right? 99 is much closer to having another digit than 11 is. So the digit function we've defined here is actually really imprecise because it treats numbers as far apart as, 9999 and 100,000 as identical, even though they're like nearly 10 times apart. But it treats numbers as close together as a million and 99999, which are just one apart, as different because they have a different number of digits. To make our digit function useful, we want to have some way of quantifying the distance to the next digit, right? Otherwise, we've got this weird rollover effect, and we can't really effectively predict when we're going to get this extra digit or not, because we can't think about this distance to the next digit, right? So what if we added some sort of like partial fractional element to the digit function, right? What if we called digit of 99999 as not being equal to 6, but being equal to like 6.9 or something. Or sorry, not being equal to 5, but equal to 5.9. Something close to 6, but having this fractional component. In that sense, if we were to multiply two lists of 9s, we could just add their digits because the fractional parts would combine and we'd get that new digit. We'd be able to predict that. Now the question is, how do we make that mathematically precise? All right. How do we know what fractional element to assign to these digit functions? Well, it turns out the best answer is logarithms. So let's say we have this function log, right? It takes in all positive numbers, so r positive, and it gives us all numbers. And it's defined by log of x is equal to the power you have to raise 10 to get x. What does that mean in practice? Well, log of 1000 is exactly 3. Notice that is equal to digit 1000. And this is because 10 to the third power is equal to 1000. And 1000 is exactly a power of 10. Log of 1111 is not something you can easily do in your head, but on a calculator is equal to about 3.046. Notice that's equal to digit of 1111 plus something small, because 1111 is pretty close to 1000. In terms of exponents, we've got 10 to the power of 3.046 is equal to 1111, because 1111 is about approximately 10 to the third, right? It has 3 more digits after the first one. And finally, log of 9,999 is about equal to 3.99996. So 5 decimal places after the 3 do we get to something that's not a 9. And notice once again that that's equal to digit of 9999, but this time plus a bigger thing, because our fractional component is bigger. And this is because 10 to the power of 3.99996 is equal to 9999, and it's approximately 10 to the power of 4. Now you might imagine that this finally fixes the rule from before, and yeah, it does. My calculator says that log of 9 is close to 0.95, and that log of 99 is close to 1.99, and log of 891 is just about 2.94. So the rule holds, and even captures the fractional digits in the product as well. Now it holds because of an exponent rule, right? 9 times 99, we just saw that that's equal to 10 to the power of 0.95 times 10 to the power of 2.94. By the exponent rule, that's equal to 10 to the power of 0.95 plus 2.94. We know that this here is equal to 891, right? So that finally gives us that log of 891 is the sum of the previous logs, as we wanted. Now log has a lot of interesting properties like this, and in subsequent videos I'll probably go through most, if not all of them. But there's one final step to take before we do that to build up our theory of logs. And that is, what if we didn't use the number 10, right? In math, there's nothing special about the number 10. It's special to us because, you know, we've got 10 fingers, 10 toes. Everything in our society uses the number 10. Our world is built on 10. But math doesn't care, right? In math, 10 is kind of just another number. So let's try not using 10. Let's define log in general, or log base b, or this little b here is called the base. And it's going to act pretty similarly to log using 10. It's going to take in the same inputs, going to have the same outputs, and it's going to be defined by log base b of x is equal to the power you have to raise b to get x. Notice that if you decide to use 10 for b, you get the same exact definition as log from before. So this is definitely just an extension of what we just discussed. To do a couple examples, we've got log base 4 of 16 is equal to 2 because 4 to the power of 2 is equal to 16. Similarly, we've got log base 2.5 of 6.25 is also equal to 2 because 2.5 to the second power is equal to 6.25. Moving on, log base 7 of 1 over 7 is equal to minus 1 because 7 to the minus 1 is equal to 1 over 7. And notice here that this is part of the power that log gives us over digit, is that we can use it on fractions and we can get negative numbers out. And finally, log base b of 1 for any b is equal to 0 because b to the power of 0 is equal to 1 for all b. And that about wraps up our introduction to logs. See you guys in the next video.